a little bit, in retrospect, the approach of to algebraic topology via differential forms, isn't always the cleanest or the most conceptual, but at the time I really loved how it directly connected with the geometry of manifolds and with questions in physics that really interested in me. So, and I think there's a lot to be said for how concrete it is. So I'd like to have applications of higher algebra that are comparably concrete, which may be a little bit of a pipe dream, but let me describe an EN algebra situation of that flavor that sort of has a very concrete connection with classical constructions. So there's the following construction. So let's let G be a Lie algebra, say a DG Lie algebra. So there's no problem with it being an L infinity algebra. And I'm working over, say, the real numbers of the complex numbers. So there's a construction. It's going to send an open set inside of Rn to the following chain complex. So the Chevalier-Eilenberg chains, so the thing that computes Lie algebra homology, of the following DG Lie algebra or L infinity algebra. So this thing here is compactly supported to RAM complex. Okay, so already we've gotten my beloved differential forms in the game. So, if you take a DG Lie algebra and L infinity algebra, you can always tensor it with a commutative algebra to get a bigger DG Lie algebra. And so we can take Lie algebra chains of this. So this is perfectly reasonable construction. It's functorial in open sets on Rn. And you can use that functoriality. If we just focus on disks, which is they give us the multiplication maps of an EN algebra. So I'm going to call this thing here, to save myself effort, that's supposed to be a blackboard bold U sub n, because I'm working in Rn of G. So for instance, if I have a picture like this, where I have a big disk D and a bunch of smaller disks inside of it that are disjoint, D1, D2, up to say dk, then the functoriality of this construction gives me a canonical map so I can multiply things in disjoint disks into the big disk. So if you do this with some care, you can extract an EN algebra. So UN of G is an EN algebra. Okay, so this is a nice concrete construction, but you might ask, why would I do this arbitrary thing, rather random looking construction? And there's a nice answer to that, thanks to Ben Knudsen. He actually shows that this construction has a universal property. So there's an adjunction of infinity categories, so infinity 1 categories, from Lie algebras, and I'm going to do chain complexes over the real numbers here, the usual tensor product, into EN algebras and chain complexes over the reals, say. So there's an adjunction UN is the left adjoint, and there's a forgetful functor, if you'd like, from EN algebras to Lie algebras. So if you want, so U n of G is the enveloping EN algebra of G. So maybe some.
So could you please slightly elaborate about this forgetful functor?
So concretely, so I don't want to describe it concretely in this particular model. It is related to the fact that if you, in characteristic 0, there's the formality of the EN operad. So the EN operad is quasi-isomorphic to its homology, which is the shifted Poisson operad. It's got a Poisson bracket of degree 1 minus n. And so, which is coming from, if you want the binary operations in the EN operad, those are modeled by a sphere, an n minus 1 sphere up to homotopy.
And
so,
you just retain the Lie bracket, right?
Exactly. Yeah, exactly. And you shift so that it's an ordinary Lie algebra if you want.
Sure.
Yeah, that's what this is doing here. So exactly. So the nice thing is that there's this sort of subtle forgetful functor, and it's got this very concrete adjoint, at least in this model. So I should say it's a really fun exercise. So remarks maybe about this theorem 1. It's a fun exercise to see how the usual enveloping algebra U of G is encoded by this one-dimensional, sort of this complicated formula. I'd be happy to talk about that after the exercise, after the talk. And secondly, I should say that Knudsen actually proves a better theorem. Allows for C, so the target category, to be an arbitrary, symmetric, monoidal, stable infinity category, possibly presentable. I don't remember all the adjectives. But here I simplified to just chains over R, because I wanted to write a specific model for UN of G. So his model specializes in that case.
Excuse me, but in the general case, you don't have formality.
Yes, exactly. So he has to do something very interesting there. So he originally wrote this for chains, or over characteristic 0, and then figured out how to generalize it. So that's an excellent point.
So there is still a forgetful functor in general?
Yes. But I would refer you to Ben's paper, because like I said, I'm a very lowbrow guy. I'm not worried about working in arbitrary spectra or something. I like my chain complexes in characteristic 0. Okay, I really like the questions and comments, so I think these are really great. So please keep them coming. It makes me feel like I'm not speaking into an empty room. Okay, so maybe
could you scroll back up to the first definition again? I want to browse it a little bit more. Sorry.
This thing here?
Very beginning. Yeah. So this depends on Rn. I mean, this looks like it could work for any target manifold. I guess you said something like that, but it's.
I was about to say that. Yeah, it'll make sense on any manifold, not just Rn.
Yeah. Okay. Thanks.
Yeah. No, that's a great point. So, so maybe a third thing to remark is this model of the enveloping algebra. You could imagine making other models, is useful for computing factorization homology. So So factorization homology, just as a comment, it's a local to global construction, and it satisfies sort of analogs of the Eilenberg-Steenrod axioms for homology. So it's a homology theory that makes sense on n, and for En algebras, it can take values on framed n manifolds. That's sort of, you compare framed n manifold with an En algebra. This construction actually works for all smooth manifolds. So for a smooth n manifold M, this is one of the things that Ben proves, is that we have this En algebra. It's actually makes sense. It's SON, homotypic SON invariant. So you can do it on, or ON invariant to on unframed things, but just plain unoriented manifolds. Can be computed explicitly by the same formula. So what I want to emphasize here is that the definition of factorization homology is some crazy colimit, crazy homotypic colimit. So it might be very hard to compute for an arbitrary En algebra, just sort of inaccessible in that description as a by in terms of its definition. But this is really nice. This is classical homological algebra. If you have some concrete control over your Lie algebra and you know how to describe differential forms, then you have a real shot at computing the factorization homology, because it's just Lie algebra chains of a concrete DG Lie algebra. So this is the kind of thing I really like. In Botan 2, one of the nice things is the de Rham complex just computes the cohomology of a manifold. You don't have to do any, resolutions or anything. Just it lets you work directly. Okay, and so this is a similar case. This is a case where you can get your hands on things. So I should say that Ben used this model to address questions about sort of like nice questions in topology about configuration spaces of points. Manifolds. So Ben's an excellent writer. I think the paper where he uses it is really lovely, and the paper where he proves this theorem is really lovely. I want to address a different kind of question to analyze or address the question of how constructions involving ordinary enveloping algebra generalize to higher enveloping algebras. So that's what Greg and Brian and I were thinking about. If you're coming from representation theory, tons of stuff can be phrased in terms of the universal enveloping algebra. There are beautiful theorems, like this is a thing we end up generalizing. There's this Harish-Chandra isomorphism, which tells you that for a reductive Lie algebra, its center is very computable and describable. Okay, so that was, that's it. We're back to the question. Hopefully you have a sense of where this question is going to live. This is the kind of En algebra we're going to study, this En enveloping algebra. We're going to try to leverage this nice concrete model to help you hone in on the particular question that really motivated me. I want to mention that my other big enthusiasm in grad school, so here's another personal confession. So other enthusiasm in grad school beyond Botan 2 and differential forms was deformation quantization. I found this picture of quantum mechanics really illuminating, that you were taking a commutative algebra, really a Poisson algebra describing your classical system, and you were deforming it to an associative algebra. Felt like a very clean way of thinking about things. So let me talk about my favorite example of a deformation quantization. So the universal enveloping algebra of Lie algebra has a canonical filtration. Inherited from the tensor algebra. So the tensor algebra is filtered by tensor powers. The kth piece is all the tensor powers of size less than or equal to k. And if you look at its associated graded algebra, that's the symmetric algebra on G, which you can think geometrically as functions, polynomial functions on the dual space to the Lie algebra. Okay. So if you want, so UG is a deformation quantization of functions on the Poisson manifold G dual. And if you haven't seen this before, there's sort of an obvious Poisson bracket here. If you have two elements, X and Y and G, you just define their Poisson bracket to be their bracket in the Lie algebra. Then you should extend by Leibniz rule to a general Poisson bracket. Okay, so it's actually a Poisson algebra. Okay, so the universal enveloping algebra has a physical interpretation as some kind of modification of a mechanical system, of a classical mechanical system living on this Poisson manifold, the dual of the Lie algebra. Okay, so this fact connects with Knudson's picture, or Knudson's construction by a Swiss cheese picture. I'm kind of assuming people maybe have seen the Swiss cheese opera ad. So draw a picture. So here's a copy of the real line, which if we're doing this physics interpretation, you can think of as time. Okay. And on it is living U1 of G, this E1 algebra, U1 of G, if you want factorization algebra, living on the real line. Okay. Which is, and this is modeling U of G. But we can think about this copy of R as the boundary of an upper half space. And then we could ask, could we put an E2 algebra in the bulk up here so that we have this kind of Swiss cheese structure? So here's a pop quiz for everybody. What E2 algebra should A be? What's the natural E2 algebra to have act on the enveloping algebra, UG? This is partly just to test if I've gauged the audience correctly. Say it again?
Is it Virchow complex?
U2.
So sorry, could just one, I don't know how to get that.
Well, you
Maybe the first person. Yeah, please.
The center of it.
Great. And by center, do you have any other names for it as well?
Hochschild parabology.
Absolutely. So the answer, a good answer, is the derived.
The derived center, of course.
Yeah, I mean, it's sort of a little bit, may seem tautological, of UG, which in this case is often modeled by the Hochschild cochains on UG, is the universal answer. in the sense that if you're going to give a Swiss cheese pair, so this is some algebra over the Swiss cheese opera, that's equivalent to giving a map of E2 algebras. So if you want an E2 algebra to act on U of G, in terms of this sort of Swiss cheese picture, you could also just give an E2 map from A into the Hochschild cochains of UG. Okay, so great. So I did gauge the audience correctly. Some people at least are familiar with this story. So the physicists also have thought about this kind of situation. So this has a physics interpretation.
Excuse me, in this concrete case, when your associative algebra is UG, is not the answer somehow connected to U2G?
It will be. Well, it won't be connected to U2G. Yeah, I'm going to give you an answer in just a minute. Maybe you can ask me once I've gotten to that answer. Is that okay?
Mm-hmm.
So this has a physics interpretation. It's what they might call a bulk boundary system for kind of obvious reasons. So this is the bulk region up here. It's in the 2D part, and its boundary is down here. So we want to imagine, to a physicist, we have this mechanical system. You know, there's a one-dimensional mechanic system as a particle running around in G star. And then there should be a 2D space-time with it as its boundary. And something's going to be happening in this bulk area. Maybe the most famous example of a bulk boundary system, for most mathematicians anyways, the Chern-Simons WZW correspondence. But there's the one I'm going to talk about here is a very nice one. So in this case, the bulk theory has a name, is a 2D topological field theory known as topological BF theory. It's essentially an example of a Poisson sigma model, which if you've studied Kontsevich deformation quantization, you'll have run into. So this is all just terminology, this BF stuff, Poisson sigma model. It's actually a very natural thing for a mathematician to think about. The classical theory is very nice, but it actually is studying, so topological BF theory on a surface sigma corresponds to studying flat G bundles on sigma, but really studying its shifted tangent bundle, cotangent bundle, I should say. So this is some kind of derived space, derived stack. Flat G bundles, if you want, is the character variety on sigma, and we're studying some shifted cotangent bundle of the character variety. So that's a thing a geometer could love. So there's this physical system, and once you have a physical system, a classical field theory, you can ask if you can quantize it. And I would say that the answer is yes, although I don't really know exactly where it's written nicely and explicitly in the literature. You can compatibly quantize this bulk boundary system to get the Swiss cheese algebra So topological BF theory admits, with this special choice of boundary theories, admits a nice deformation quantization, if you want, that recovers the Swiss cheese thing. And I think this is something really remarkable to me. If you've ever done Feynman diagram computations, you'll know how combinatorially and analytically messy they are. So it should be kind of a surprise that you can do that construction and get something that admits a universal property. So I think this is really remarkable. There are quantum bulk boundary systems whose observables satisfy a universal property. I think this is important from the point of view of physics because it explains sort of conceptually why sometimes we get these very nice results with bulk boundary systems. They satisfy universal properties, so there's something canonical about them. They're not just some ad hoc thing somebody's done with in some tour de force of combinatorics and analysis. Okay, great. So, so my two early obsessions kind of converge here. We've got to this kind of question. Given our beloved EN algebra, the EN enveloping algebra, what is its universal, which we can think about as a quantum system? This thing is naturally filtered, and so it has an associated grade, which is very simple. It's universal bulk theory, aka its derived center. Okay. What I'd really like, in fact, is a concrete model for the derived center, comparable to Knudson's very concrete model for the derived center. So let me I'm going to sharpen that question just a little bit. So I'm going to follow Lurie. Although I'm sure there's lots of predecessors to this definition. It's where I've seen it formalized this way. So let me say what I mean by derived center. For a map of EN algebras F from A to B, its centralizer, which I'll write as scripty C sub n of F, is the E sub n algebra universal among those fitting into a commutative diagram. I'm just going to draw the one that's relevant here. So we have A going to B via F. We can take the tensor product of A with some other EN algebra. In this case, I'll write the one I care about. These are unitals, so you can take the unit in Zn of F, tensor the identity on A. So there's a map of EN algebras that goes from A up into here just by putting one here and copying. And so you need to find a map that commutes. Okay. So I'll unpack that in just a second. The center of A, which I'll write like this, Zn of A, is the centralizer of the identity map. Okay, so I'm just going to give a plausibility check. This definition is reasonable. So I'll leave it all there. Let's suppose that n was 1, so we're just doing E1 algebras, and I'm just going to take my category to be plain vector spaces. So I'm really just thinking about ordinary associative algebras where we have a good feel for the center. So suppose I have a map of associative algebras F from A to B. What would it mean to find a map phi of algebras from Z tensor A to B that factors like this? Well, so here A, if you go up, goes to 1 tensor A, and then it goes to F of A, which is phi 1 tensor A. But I want you to just notice that if I take some other element, little z in Z, there's two ways to compute this. On the one hand, you can factor Z tensor A as Z tensor the identity, tensor 1 tensor A. And this becomes phi of Z, phi of A. But because Z and A commute in here, this is the same thing as phi of 1 tensor A. I should put a dot, so it's a dot. Dot Z tensor 1. And this is phi of A, phi of Z. So if I can make a commuting diagram like this, then the image of phi of Z inside of B has to commute with the image of phi of A. But phi of A, of course, is just F. Okay, so if this was the identity, this is literally asking for the center. So this is a nice generalization of the notion of center. People sometimes call this commutant for the relative case. Okay, so remember, we just defined what we mean by centers and we generalized it to the notion of centralizer following Lurie. And so now I can formulate what I really want to say here is, if I have UN of G, what is its EN center? And more generally, if I have a map maybe of enveloping algebras, what is the centralizer? So this is maybe the main theorem of the paper with Greg and Brian. Maybe before I state it, I should give a shout out, although I'm not explaining the contribution. So Bruno Valette, Ricardo Campos, and Pedro Tamaroff have helped us improve the proof considerably by using some operatic calculus. I'm not going to display that part though. So here's the theorem. So thank you, Bruno. Let G and H be DG Lie algebras. And let's say that F is a map of DG Lie algebras. Okay, this determines, of course, a map functoriality from the enveloping algebra of G to the enveloping algebra of H. Okay, now the crucial thing for us, the crucial thing we show is that the centralizer of this map has a very nice model. It's very much in the same flavor as what I wrote, as what Ben wrote for just UN. So I'm going to write it and then I'll comment on it. Okay, so this part is just Ben's nice model for UN of H. So F determines how the DG algebra to Ramform's tensor G acts on UN of H, right? I mean, we fixed a map here. So there's some way in which G acts on H, and that extends to how it acts on UN of H. I want to point another change. here we have Lie algebra. On the right-hand side, we have Lie algebra chains, but here we have Chevalley-Eilenberg cochains. Okay. And notice that we've also changed from compactly supported RAM forms to non-compactly supported RAM forms. But in the end, the point is that the centralizer of this map has a very nice model in terms of classical constructions to RAM forms and Lie algebra chains and cochains. Okay, so in particular, the center here is quasi-isomorphic to the Lie algebra cochains of G with coefficients in UN of G via the adjoint action. So as a remark, when n equals 1, it's a classical fact that the Hochschild cochains of UG is quasi-isomorphic to the Lie algebra cochains of G with coefficients in UG via the adjoint action. So this is some generalization of this classic fact. Okay.
May I ask a question?
Of course, please.
The left-hand side is a En+1 algebra, right?
Ah, yes, you're very good at anticipating what I'm going to talk about next. Absolutely.
Okay, thank you.
So this is actually an En+1 algebra. This is part of the Deligne conjecture package. So we get, if you'd like, a Swiss cheese pair. Zn of the center and the enveloping enveloping algebra. Okay. So this talk is going much faster than I thought it would. So what would be the best thing to say here? So that's the main theorem, is that we have this nice generalization there. Are there any questions before I sort of go on into some consequences of this? So first off, we've sort of answered part of my question. One of my questions, we've given a nice model, concrete model for the factorization, for the derived center of the enveloping algebra in very explicit terms. Okay. So let me turn to some consequences of this. Because this model is so explicit, you can extract some concrete consequences. You can really get your hands on things. So maybe the one quite immediately interesting to me, but maybe not to everyone, is that topological BF theory on n+1 dimensional space admits a distinguished quantization where its quantum observables are equivalent to the En+1 algebra, which is the derived center of UN of G. So this is this situation I was saying I wanted to generalize. So the boundary space-time is Rn+1, and then you can imagine you have the bulk up here, the n+1 dimensional half space, and the observables down here, The boundary observables are UN of G. And the bulk observables up here. Let's see. Okay. So that first story about how there was this Swiss cheese, this I think this is it was a conjecture of Kontsevich, so it was eventually proved that there was this that the Hochschild cochains is the derived center and fits in this Swiss cheese package, fit in nicely with his approach to deformation quantization. And this is a sort of systematic generalization, at least in this case. I should remark that the key point to bear in mind is that U in G is canonically filtered. By using the filtration on Lie algebra chains. This lets you see, and sort of, so I should say that on a disk, it's easy to see that this looks like sim of G, shifted by 1 minus n. So you can see that when n equals 1, this is the case we saw before for UG. This has a natural shifted Poisson bracket. Yeah, please.
I'm a bit lost. What is the filtration here? I do not get it.
Oh yeah, you should get this. So F K C star Lie of any Lie algebra is this part. It's just the lower symmetric powers of degree K or less, and the differential preserves that filtration.
Perfect. Thank you.
Yeah.
And this gives filtration by, well, I don't know how to formulate the question. Classically, you have a notion of filtered associative algebra, which has a requirement of correspondence between filtration and the operation. What is it here?
Yeah, exactly. So the filtration, so this is a filtered EN algebra. You can just check that the maps, the multiplication maps in the EN algebra respect this filtration, because you're just using wedge product of differential forms.
So you just naively write down the formulas and they make sense, right? You
exactly.
Mean
that's
product.
Yeah.
There
It's
is
just
more or
such
less
on
only
the
one
nose.
product, but
yeah, exactly. Well, so that's one of the things, is that when you write it in this way as a functor on all opens in the manifolds, or even on there's a colored operad where the colors are the opens in the manifold, you know, you sort of spread out the information in a very convenient way so that you can use these on the nose constructions. It's harder to see that filtration if you use certain other models of the EN operad.
well, yeah, exactly what I wanted to say, that for me, EN algebra is something very homotopical thing. And I cannot even imagine how to define what is a filtration.
Right. So I think that's the kind of, I totally get your point. And it just happens to be the case that in this thing, you can write really barehanded things with values in filtered complexes, and it all works out, like totally barehanded filtered complexes. Maybe I should make a remark. There's an operad. I don't know if I'm going to remember the name. In Laurie's higher algebra, he gives a very nice treatment of the fact that there's this, I still remember the notation he uses. There's a colored operad generated by disks in, say, Rn. It's a totally discrete colored operad, and you can make an infinity operad out of it, and then localize at the inclusion of a smaller disk into a bigger disk. And when you localize in that infinity operad setting, you get an infinity operad quasi-isomorphic to, or quasi-equivalent to any other model of the En operad that you care for. So it's some convenient model, and I'm really leveraging that in this construction. Yeah, anyway, look, there's a filtration, and in that sense, you can see on the boundary, you can see this is a kind of quantization, and the bulk also has a natural associated filtration. And so you can see this quantization in those terms. There's no Feynman diagrams, no in this process. Okay. Various classic results in Lie theory generalize. I'm not going to elaborate on these, mostly because the notational overhead gets a little annoying. But so the Harish-Chandra isomorphism I mentioned before, which is that for G reductive, the usual center of the enveloping algebra is isomorphic to the symmetric algebra, the Weil invariant Weil invariant piece of the symmetric algebra on the Cartan generalizes. In an appropriate sense. So there's some explicit description of the very concrete description of the En center of the En enveloping algebra of a reductive group. And as you might expect, another classic result you can revisit is Cazul duality. Cazul duality can be seen as thinking about.
Excuse me once more. Excuse me once more. Once
Please.
once you apply this for the case n equals 1, you shouldn't get classical center, you should get derived center. So
You do, but
once
there's not a whole lot
so
going
it's
on
not
for
really a
reductive.
generalization, right? There is no
I
Harish-Chandra.
There is. I mean, there's nothing deep here.
Okay.
So if G is semi-simple, I'm going to ignore the slight complexity of reductive, then the Lie algebra cohomology with respect to any module oh, sorry, I did that backwards. Looks like the strict invariance tensor with the Lie algebra cochains of G. There's just the derived endomorphism, the algebra cohomology of the trivial rep. And so you can refine this if you want. And so the only extra junk you get from the center, sort of coming from the pure Lie algebra cohomology part. This whole piece here is here. So there's not a whole, I mean, part of it is just the Lie algebra cohomology for reductive things and semi-simple things isn't that interesting as maybe part of the point. But I am curious if there's some useful consequences in representation theory for this kind of silly fact. You can revisit Cazul duality. Cazul duality can be thought of as, some versions of Cazul duality can be thought of as studying centralizers of augmentation maps. So this is Zn of the augmentation map. To the base field. This is quasi-isomorphic to the Lie algebra cochains of G as En algebras. Maybe just to finish up, I'm trying to survey some applications. Hopefully it's imaginable how they would be, why having an explicit model would make your life particularly easy. So there's applications to factorization homology because we have this explicit fact, and that's related to Kontsevich calculus. So Geoffroy Horel has a very nice paper about this. So an example of the kind of thing you can prove, because we have this nice particular model is the following. So let's say that you have a codimension K manifold. So an n minus K dimensional. And I want it to be closed. I don't want it to have any boundary. Then there's a canonical map from the factorization homology over that n minus K manifold of the center to the EK center of the factorization homology. So if you take an EN algebra and you take it, or this EN algebra, and you take its factorization homology over this n minus K manifold, you get left with an EK algebra. And so you could ask about its EK center. And the claim is that this is actually a weak equivalence. So, so that's actually a really powerful fact about how, if you'd like, sort of the slogan might be taking the center commutes with factorization homology. And there's further consequences of that, that relationship. So I think that's probably a good place to stop. I know the last bit was quite rushed, but hopefully it's clear. I think there's a ton to do here. Now that we have enveloping EN algebras of Lie algebras to ask about what we can do with them. And we've just gotten started. Be delighted to talk with people about that. So I'm finished. Love to answer any further questions.
Thank you very much for this nice talk. No. Could you please leave? No. Come back.
Okay, I'm back.
Yes, please. Is there any question? I mean, I have a question regarding your last slide, but is there any question first? Feel free. Well, if not, I'm sorry, I'm a bit lost on your causal duality. On the left-hand side, you have an EN algebra. Fair, you take its causal dual, but I do not quite understand the right-hand side. G is a Lie algebra, and you're taking the cochain complex
This
of
part
that.
here?
Oh yeah, so
yeah.
So because
So
you shift G and you take the free symmetric algebra on that, you shift G to the n or n minus 1, and then you get a small EN algebra. Why is it an EN algebra? I'm a bit lost.
So
you probably have to think about this as Poisson thing. You take a Lie algebra and take free. No? I'm trying to guess.
This is just plain commutative.
Yeah.
A priori, this is just a commutative DG algebra.
Yeah.
And you can forget it down to an EN algebra if you want. And so,
yeah.
So this is an analog of a result you know for the n equals 1 case. You know that the enveloping algebra UG has a co-commutative coalgebra structure, and so its Cazul dual ends up being commutative, and it's this thing. And so the sort of remarkable thing is that the Cazul dual of the EN enveloping algebra is the same. So I think this is partly why EN enveloping algebras are so manageable, is they're all Cazul duals to the same object.
I think I'm okay. I think of it.
Yeah.
So Ima is asking on the chat, are you able to get some Tanaka-Krein results?
No, I haven't. We haven't tried to do that. I think that would be really, really interesting. That's a great question.
Is there any other question? Feel free. No. Well, so maybe we can thank Owen again for this very nice talk. Thank you very much, Owen.
Yeah, thanks for the chance to talk.
No, thank you. That was great.